Cartesian trees is a form of tree that is very intimately connected to the range minimum query problem, as you'll see in a second. It's a little more natural to describe this, this connection if you look at range maxima instead of minima. Of course, range maxima is really the same thing as range minima. You could take your array and negate all entries, or you just flip the comparisons. So very same thing. I'll just swap the notation here because it's slightly more natural. So here is your array, and now we're looking for the largest element in a range. Everything else is the same. So here's why I like maxima, because then I can take a bar of the height of the number shown there. If I now pick a range there, the highest bar, so the first, if I let a line that stretches the entire rectangle sink down from infinity to a certain point, it will eventually hit one of the bars, and that's the range max. Maybe I should really use our MQ with a capital M for the maxima. We won't really need that notation, so it's not that important. All we need from this section is the trees that come now. Okay, so one more time. I can take a range, I can slide down this line, and then it will hit the largest element in that range. Okay, our task again is to pre-process the array and then answer those queries fast, like before. Now, instead of fiddling with these numbers directly, I'll do something entirely different and slightly crazy. I'll construct a binary tree by keeping a line that spans the entire range and sliding it down. Eventually, this line will hit the largest pole of all, and this will become the root of a binary tree. Okay. Once I hit the root, the line splits. There's one line that's on the left and another one on the right, and those independently slide down, until again they hit the highest pole, which they did in these cases. And then at those two, the line splits again into two parts, and it will hit another pole first, so this one's slightly higher. And you keep doing this. Whenever you hit a node, that splits the line into two parts, and it slides down independently. That way you can construct a tree, and this tree is called the Cartesian tree of the array. So one more time, you build it by finding the global maximum, 16, and that position becomes the root of a binary tree. Then there's a range left and right of the root, which you recursively split. And so again, you find the maximum here, that's the next node, and then that splits again the array into two parts. And you recurse on these. That's how you find the Cartesian tree. Last thing why this is useful is range-min queries in the array are the same as lowest common ancestors in this tree. How is that? If you take the node that's corresponding to the left and right endpoints of our query range, those are the highlighted nodes in the tree, then the maximum is their lowest common ancestor, and that's the node 10. Isn't that magic? We've seen the connection that range-min query has something to do with lowest common ancestors earlier when we talked about the connection to suffix arrays and the longest common extensions there. Here it comes up in a different form because the tree is different. Suffix trees are not necessarily binary, and we were looking at lowest common ancestors of leaves. But apart from that, it's a very similar notion, and very similar reasons are behind why this connection exists.